Write down this heading, total internal reflection. Okay. So now what is total internal reflection? When a ray of light, or when the light moves from a source which is kept in denser medium into the rarer medium, then we know that, say, this is a source of light, and from here the ray which goes straight goes undeviated wherever. If a ray is incident at a certain angle, it will bend away from the normal because it's moving from denser to rarer medium. So if we increase the angle of incidence in denser medium, angle of refraction in rarer medium will also increase. So we will get actually a angle of incidence, an angle at which the ray will be incident in denser medium, for which the ray will become parallel to interface. Okay? Ray will get parallel to the interface. And if the angle of incidence increases, then the angle of refraction will be more than 90 degrees. That means we are getting an angle where the angle of refraction becomes 90 degrees. Okay? And if we increase the angle of incidence more than this stage, the angle of refraction should be more than 90. That means ray will get refracted back into the same medium. Okay? This angle at which this angle of incidence in denser medium, for which angle of refraction in rarer medium becomes 90 degrees, okay, is called critical angle. So theta c is critical angle, that is angle of incidence in denser medium for which angle of refraction in rarer medium becomes 90 degrees. Okay, or we can say ray become parallel to the interface. Okay, or we can say refracted ray become parallel to interface. Parallel to interface. Okay. So if angle of incidence become more than critical angle, then instead of going to the rarer medium, that is other medium, ray will get bounced back or reflected back into the same medium. This phenomena is referred to as total internal reflection. Okay. So we can say that when angle of incidence in denser medium, when angle of incidence in denser medium is greater than critical angle, okay, the ray will get reflected back into the
Ma'am, this
same
can
medium.
only happen. This can only happen if it goes from denser to rarer.
Yeah, it can only happen if it goes from denser to rarer. The ray will
Yes,
get reflected back into the same medium. This phenomena is called total internal reflection. So conditions for TIR becomes number one, ray should move from denser to rarer medium. Okay, number two, angle of incidence greater than critical angle. Okay. Now it is called total internal reflection because the ray of light is 100% reflected into the same medium. Okay. It's called TIR in total internal reflection. Ray get 100% reflected back, okay, in the same medium. Now what this statement means, we have learned this thing that whenever the ray falls on a interface or on a surface, absorption, reflection, refraction of light can happen. So that means whenever the ray is incident on an interface, transparent interface, the major phenomena is refraction. So maximum intensity of ray will refract, but there will be a small intensity which will get reflected. Whenever refraction is happening, some reflection is also happening. But when we are saying it is TIR, 100% rays are reflected back. There is no refraction, there is no absorption of light happening. Okay. So in TIR, 100% reflection of the ray is happening. Okay. Because of this only, uh, we use optical fibers in which TIR is a major principle in by which the optical signals are being transmitted from one point to another point. Okay. So what is optical fiber? There are thin fibers, yeah, transparent structures. Say I'm giving you the simpler one in which we are having a transparent core surrounded by another transparent medium. That means there is a cylindrical central core transparent medium. ठीक है, cylindrical medium which we call as core, and surrounding this cylinder there is another cylindrical transparent medium which is called as cladding, and this core and cladding is then further protected by the cover of jacket and so that the strength can be maintained. So the central point is called core, and surrounding medium is called cladding. Say refractive index, uh, will be more. That means this will be a denser medium and this will be a rarer medium. Okay. When the ray is incident on the core at an angle more than critical angle, the ray will experience TIR, and in this way, this optical signal will get transmitted within the through the optical fibers. Okay. Now, instead of using this fiber arrangement, we can also have plane mirrors. We have discussed such questions where we can have two parallel plane mirrors, and if the ray is incident on one mirror, after multiple reflection, we can obtain the signal on the other side. Then why we use optical fiber and why we are not using this plane mirror? It's because in case of mirror, there will be some absorption also, which will be happening side by side. So greater the length, that means if more the number of reflection happening, more absorption of light will happen. That's why on the receiving end, the intensity of the signal will be very less. Okay. And hence we won't be getting a strong signal. Whereas in case of this fiber, optical fiber, since 100% rays are getting reflected back, therefore the intensity on the receiving end will be quite high. And thus we use optical fiber for the transmission of the optical signals. Clear?
Ma'am,
Yes, Peter.
ma'am, does TIR follows the laws of reflections?
Yeah. During TIR, laws of reflection are followed. At whatever angle the ray is incident, it will get reflected back, making the same angle. So here I will be equal to R. You can write down this point also. During TIR, laws of reflection are followed. That is, the angle at which the ray is incident, it will get totally internally reflected, making the same angle with the normal.
Excuse me, ma'am.
Yes, Peter.
Ma'am, in TIR, Snell's law follows.
No, Snell's law will not follow, no, because Snell's law is when refraction happens. So there is no refraction happening here. Only
Okay.
reflection is happening.
Now, what the blue part represents in that?
It is jacket or covering, protective covering. We call it as jacket.
Ma'am, before cladding, what have you written there?
Core, then cladding. CORE, core. CLADDING.
Yes, ma'am.
All of you written all these points?
Yes, ma'am.
Now let's discuss a question where say we discuss a concept side this. Let's say uh, there is a source of light, okay, in a swimming pool. So you'll be able to see the light around it, but there is a level after beyond which the rays are not getting refracted. Why? Because say this is a source, then what will happen? The ray, when incident at an angle greater than critical angle, it will experience CIR. So if you are able to see that light source, this is because the light rays which are falling on the interface within this circular disc, because it will be the rays will be falling on the, on this circle anywhere, making an angle of more than critical angle, just more than critical angle, or it at a critical angle, it will become parallel to principal axis. Sorry, क्या बोल रही हूँ? If it is incident on the critical angle, it will become parallel to this interface. Okay, so I can draw like this. Interface वाला कैसे करते हैं? So at this angle, if it is incident at critical angle, the ray will get parallel to interface. Okay, and an angle more than critical angle, it will get internally reflected. So that means if you are able to see this source of light in water, it is because rays are coming out into the other medium within this circular disc. Okay? So if by anyhow I can cover this complete transparent part from where the rays are coming outward, because beyond this circular disc, the rays will experience CIR, so no ray from the source will come out of the water, okay, into the air. So that means if I cover this complete circular disc from where actually rays are coming out from water into the air, then we won't be able to see the source of light inside water. Is this point clear to everyone? Are you getting this thing?
Ma'am, can you repeat that covering
Right.
part?
Yes, beta, again repeat.
Ma'am, can you repeat that covering part again?
I'm saying that say this is my source of light, okay, which is say inside the pool of water. Now, if there is a light source, we are standing anywhere around the pool, we'll be able to see this light source. But truly speaking, there's only a certain, certain circular area from where these rays are coming out of the water. Why? Because the moment the rays are incident at an angle of critical angle or more, the rays either will become parallel to the interface or will internally reflected. So that means if the angle of incidence is either equal to critical angle or more than critical angle, we'll never get a ray which is coming out in the air. So the rays, if they are coming out in the air, they are coming out within this circular disc. Okay? That means if the angle is less than critical angle, if the angle of incidence in the denser medium is less than critical angle, then only the ray will get emerge out into the air and you are able to see the source of light. Okay? Is this point clear?
Yes,
So,
ma'am.
so now if it is being asked that what should be the radius of this circular disc or what should be the area of the circular disc, we can calculate such question. Okay, let's do this thing, that at what depth the object should be kept, and all these relations, let's discuss this thing. So this type of question will be, can be done using the concept of total internal reflection. So say this is interface and here is my object, the source of light. And say here the ray is incident at critical angle. This angle is critical angle. This is refractive index of denser medium, refractive index of rarer medium. And say the object is at the source of light is at a depth of d, and r is the radius of this circular disc. Okay? R is radius and d is depth. Okay? So S, and this point is A, this point is say P. Right? Now using Snell's law at point P, okay? Using Snell's law, at point P, we get here that ND into sine theta C is equal to NR into sine 90. So we can say sine theta C is equal to NR upon ND. Sine 90 is 1. Okay. So sine of critical angle is equal to, I can rewrite it as N dr ND upon NR, that is equal to 1 upon N dr. So critical angle can be given as sine inverse of 1 upon refractive index of denser medium with respect to rarer medium. And if rarer medium is air, ठीक है, इसको R की जगह ना capital R करो, so that we are not getting confused, because we are using small r for rarer medium. ठीक है, R stands for rarer medium. If a rarer medium is air, ठीक है, then refractiveness of rarer medium becomes 1. So now we can say then refractiveness of denser medium will actually be the refractiveness of the medium. So I can also write it as critical angle can be given as sine inverse of 1 upon refractive index of the medium, denser medium. ठीक है, absolute refractiveness of denser medium when my surrounding medium is air. ठीक है, rarer medium is 1. Got it? This point is clear. Okay. So now let's discuss this thing. So this angle is theta c. So this angle will also be theta c. We need to find out the relation between D and R. So I'm using here tan of angle theta c can be given as R upon D. Okay? R upon D. So I can say R is equal to D into tan theta c. Now to find out the angle of tan of angle theta c, we can use this relation of sine theta c is equal to 1 upon dr. Okay, using this relation of Snell's law, you can find out as यहाँ पे कर रही हूँ, as sine theta c is equal to 1 upon refractiveness of denser with respect to rarer. If I have a triangle for angle theta c, which is ratio of perpendicular upon hypotenuse. Sine is ratio of perpendicular upon hypotenuse. So perpendicular become 1, hypotenuse become n dr. So base will become under the root of n dr minus square minus 1. Okay. So from here I'll get tan of critical angle will be given as perpendicular upon base. So tan of theta c will be given as 1 upon under the root of refractiveness of denser with respect to rarer square minus. What is the value here? So I'll get here radius will be given as d upon n dr square minus 1 power 1. Okay. This will be the radius. And if it is asked what is the area of this circular disk, then we know the radius, we can find out area using the formula pi r square. Okay. So you can get any combination of question from using this concept. Either they have given us the radius, they can ask us to find out the the depth of the source from the interface. They have given us depth, they have given us radius. They can ask us to find out the refractive index of denser with respect to rarer medium. So any of this unknown can be asked. So if the concept is clear, I that you can solve such questions.
Excuse me, ma'am.
Yes, beta.
Ma'am, if we like close that circular disk, will we not be able to see its virtual image? Like convergent beam of light will be in
No, we
total
won't
internet.
be able to see the source. We won't be able to see the source because we are able to see the source of light only because the rays are coming from the source and reaching our eye. It will cover the complete region from where rays are actually getting refracted. Then no ray of light will get refracted into the air and hence we won't be able to see the source.
Like ma'am, the rays which get totally internally reflected,
Hmm.
we like extend them backwards, and at some point they will meet.
No, no. If you have ever seen the ray diagrams which we have plotted, then the rays are getting diverging. Diverging rays are actually reaching the eye of the observer. We say that these rays are not actually meeting at a point, but for the observer, since rays are reaching his or her eye, so to the eye, it appears that there should be a point from where these rays are starting and there the virtual image is formed. In this case, no ray is reaching in air, is not coming out in air. So that means the rays which are like this rays which you are saying will be reflected back if the rays are coming incident at an angle greater than critical angle. You are standing here. Is any ray reaching your eye?
No,
You are
no.
standing here. No? So when there is no ray which is actually reaching your eye, then the image won't be formed. You won't be able to see the object. Whether it's a real image or a virtual image, that depends upon the when the rays are and reaching your eyes, either the rays are diverging or the rays are converging. Depending upon the scenario, you can see the object. Okay?
These rays are diverging like
But these rays are not reaching the eye of the observer. No? The
okay.
condition is that the rays should reach your eyes. If you want to see the object, there are the reflected or the refracted rays which are reaching your eye. If rays are not reaching you, will you be able to see the thing?
Yes.
Got it? Done? All of you have done this solution?
And what will happen if the critical angle is not on the edge?
Not on the edge means?
Like in the figure you have drawn,
Hmm.
if it is between this disk, inside this
No, no,
disk,
better if
then
whatever is the critical angle. Why I've drawn the disk? I'm saying disk is the reason from where the rays are actually coming out. This disk represents the complete area from where the rays are actually getting refracted. Beyond this disk, the rays are not getting refracted. This is what I'm telling you.
okay.
Okay. That is this question. Its speed of light. I space 2.3 into 10 raised to power 8 meter per second. What is the critical angle of incidence, critical angle of incidence for light going from I to A. We have discussed the relation of critical angle and refractive index.
Sine inverse of 23/30.
Sine inverse 23/30.
Critical angle for the, sorry, refractive index for ice will be given as P upon within ice. That means 3 into 10 raised to power 8 upon 2.3 into 10 raised to power 8. That is 30 upon 23. Now we know that sine of critical angle is given as 1 upon refractive index of denser with respect to rarer. Okay? That is, I can say refractive index of air upon refractive index of ice. So theta c comes out to be sine inverse of, since air has a refractive index of 1 and ice we have calculated 30 upon 23. Okay. So it will be sine inverse 23 by okay. With this, our syllabus is done. Okay, I'll be taking your doubts from the package also. We'll be taking the quiz in Glorify. Okay. I think so. This mirror, convex, concave mirror concept is clear to everyone. Yes, all of you, are you comfortable in the concept of concave and convex mirror?
Yes, ma'am.
So, will you be comfortable in giving a quiz on this topic?
Yes, ma'am.
ठीक है then. See your this your Glorify. Go to your Glorify. I'll enabling a quiz over there. ठीक है. And you all have to give that quiz.
Right now?
Yeah, right now. It's a 20-minute quiz. Don't submit it before 15 minutes. Even if you have completed the quiz, don't submit it before 15. Matlab, when the time is 15 minutes, then only you will submit it. Okay? So,
Ma'am, have you assigned the test?
I'm just assigning. It will start at 5x sharp.
Okay, thank you.
Ma'am, when will it start?
Hmm. Okay? So the quiz will start. All of you have received the message?
Yes, ma'am.
Yes,
Okay.
ma'am.
So it will start, I think, so in next 2 minutes. You all have to give the quiz.